Welcome back to my office hours. In this video, we will show the solutions for two example problems regarding the use of the viscosity equation. The viscosity equation, as shown here, connects the shear stress with the dynamic viscosity of a fluid through its velocity gradient. At the same time, the dynamic viscosity has been used to define the kinematic viscosity of a fluid after it is divided by the fluid's density. We have a separate video posted earlier that is dedicated to explaining these basic concepts. Here, we will use two examples to demonstrate the applications of the viscosity equation. Problem 1. On a level stationary surface, a fluid with a specific gravity of 0.8 has a kinematic viscosity of 4 × 10⁻³ square meters per second. When the fluid is spread on the surface, it forms a thin film layer of 1 mm. A mobile thin plate, which has a length of 30 cm, width of 10 cm, and height of 0.1 cm, is positioned atop the liquid. Question: what force in the unit of Newton is required to propel this movable plate at a constant speed of 10 cm per second? Solution: as we were told, the moving plate is moving at a constant speed as it is being pulled by an external force. This external force is unknown. However, if an object moves at a constant velocity, its acceleration is supposed to be zero. According to Newton's second law, the sum of all the forces along the direction of this movement should be zero. Back to the moving plate in this problem, there are only two forces along the direction of its movement. One is the applied external force that is unknown. The other is the drag force as a result of the fluid's shear stress. And as we discussed before, the shear stress is linked to the viscosity by the velocity gradient. Now the solution process is clear. If we want to find the unknown external force, we must calculate the drag force. To calculate the drag force, we need to know its shear stress tau, and the surface area on which this shear stress applies. We can easily calculate the surface area because we know the dimensions of this moving plate. So our focus now is how to calculate the shear stress. To calculate the shear stress tau, we will need the viscosity equation. In the viscosity equation, we need to know the dynamic viscosity μ, but we are only provided the kinematic viscosity νo. Therefore, we will have to calculate the dynamic viscosity from the kinematic viscosity. We are told that this fluid has a specific gravity of 0.8. According to the definition of specific gravity, it is the ratio between the density of the fluid and the density of water at 4 degrees Celsius. The density of water at 4 degrees Celsius can be found from the literature easily. Hence, we can calculate the density of this fluid, which is about 799 kilograms per cubic meter. Using the density of this fluid and the kinematic viscosity of the fluid, we can now calculate the dynamic viscosity of the fluid. The result is about 3.2 pascal/second. In order to use the viscosity equation to calculate the shear stress, we will also need to find the velocity gradient in this problem. Because the liquid layer is very thin, the y-axis increment delta y is considered very small. The fluid having contact with the stationary surface is almost stationary. Whereas, the fluid having contact with the moving plate is moving at nearly the same speed as the pâté. Hence, the velocity difference delta v is approximately the speed of the moving plate. Therefore, the velocity gradient is 100 per second. Substituting the dynamic viscosity and the velocity gradient, we can now find the shear stress tau. It is approximately 320 pascal. Knowing the bottom area of the moving plate has a length of 30 cm and a width of 10 cm, we can calculate the area A. Finally, shear stress times the area gives us the drag force, which balances with the external force applied. And the result is approximately 9.6 Newton. Problem resolved. Now let's take a look at a different problem for the viscosity equation. A plate is smoothly sliding down an inclined plane at an angle of 30 degrees to the horizontal, maintaining a constant velocity of 0.8 meters per second. The plate has an area of 0.8 square meters. A fluid cushion, with a thickness of 0.1 mm, exists between the plane and the plate. Determine the viscosity of the fluid in poise given that the weight of the plate is 280 Newton. The unit conversion is 1 Pascal second equals to 10 poise. The solution for this problem is more straightforward. Along the direction of the constant speed movement, the drag force caused by the shear stress is balanced with the gravitational force downward the slope. The gravitational force downward the slope can be found by analyzing the slope's angle, using gravity mg multiplied by sine 30 degrees. Therefore, it is known that the drag force related to shear stress is 140 Newton. Shear stress is the drag force divided by the contact surface area 0.8 square meters, so we can calculate the shear stress being 175 Pascal. Back to the viscosity equation, we just need the velocity gradient in order to calculate the dynamic viscosity, and the method to calculate the velocity gradient is the same as we previously discussed. Therefore, the dynamic viscosity of this unknown fluid can be calculated by rearranging the viscosity equation. Thank you for watching. Leave a comment if you like to see more videos with example problems.